Alright, let's do an introduction to Chapter 12. Many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? To investigate, an AP Stats teacher randomly assigned students to seat locations in his classroom for a particular chapter, recorded the test score for each student at the end of the chapter. The explanatory variable in this experiment is which row the student was assigned, row 1 being the closest to the front and row 7 the furthest away. Do these data provide convincing evidence that sitting closer causes the students to get higher grades? Now obviously it can't be a causation, but is there an association? So look at number 1. Describe the association shown in the scatter plot. So I'm using my DOFS acronym and I'm looking at it. It looks like it's negative, it's weak, it's kind of linear, but there's no outliers. So my answer would look like this. There appears to be a weak, linear, and negative association between the row in which a student sits and their test score with no apparent outliers. Number 2, using the computer output, determine the equation of the least square regression line. So remember my two variables. X is the row number, Y is the predicted score. And looking at my table, I'm looking at these two values. This one is my row number, so that's my explanatory, and the constant is my y-intercept. So this is my slope and y-intercept. So my equation looks like this. Y hat equals 85.706 minus 1.11718x. I can keep it as y hat and x because I've defined the variables here. You could put the variables in the equation if you wish. Number 3, calculate the value of the correlation. Remember, correlation is just r. The table doesn't tell us r, but it does tell us r squared. So what we need to do is convert this to a decimal, this percentage, and take the square root. So when I do that, I get 0.22. Now I have to decide, is it positive or negative in the association? And the way I'm going to know without a scatter plot, which I have, but I also can tell from the slope of the line. The slope of the line is negative. So I know that my R value is negative 0.22. Number 4 says, calculate and interpret the residual for the student who sat in row 1 and scored a 76. So I look at my line, or my question, and it tells me that the X variable in this situation is 1, because it's row 1, and the Y variable, or the response, is 76. But this is the actual value. This is not the predicted, this is actual. To interpret residual, I have to do actual minus predicted. So I need to find my predicted by taking that 1 of x and plugging it in my equation. When I solve it, this is the predicted score using the regression line. So actual minus predicted, I take the actual right here, subtract what I just calculated, and I find out it's negative 8.59. Now I've calculated, now I have to interpret. And I would say the student scored 8.59 points lower than expected based on the row they sat in. Okay, notice I don't say negative 8.59. The negative is understood when I say lower than expected. Number 5, interpret the slope of the least square regression line. So we already found slope right here. It's the negative 1.117. And I have to keep in mind, what is the explanatory variable? It is the row in which they sat, right? So my interpretation would look like this. For each additional row a student sits away from the front, the predicted score decreases by approximately 1.12 points. Okay, remember it's predicted score. Number 6, interpret the standard deviation of the residuals. That's the S value right here. So I would say, when using a regression line where x is the row number to predict the y, the test score, we will typically be off by about 10.07 test points. Okay, that's what S is referring to. Number 7, interpret the value of r squared. Well, again, we already saw r squared right here in the table, so we just got to put the correct interpretation. It would look like this. 4.7% of the variation in test scores is accounted for by the linear model relating the row number to the test score. All right? So remember, it's whatever percent of the variation in the response variable is accounted for by the linear model relating explanatory to response variable, obviously in context. Number 8, explain why it's important to randomly assign the students to seats rather than letting each student choose his or her own seat. Well, if students choose their own, the more studious might choose the front rows. This could make it look like sitting closer to the front causes higher scores. By randomly assigning seats, it's more likely the average ability in each row is approximately the same. And that's what we want. And lastly, what other variables did the teacher control? And what's the purpose of keeping these variables the same? Well, there's several they actually controlled. Same test, same amount of time, same teacher, you could say same classroom, level of distractions, all those things. Now what's the purpose of this? Well, it helps reduce the variation in the response variable due to other factors, distractions, grading methods. If we can reduce variation, it increases our R-squared value, and it decreases our standard deviation of residuals, which makes it easier to see an association.